Good afternoon, everyone. Welcome to another Atom seminar. Today we have the pleasure to welcome Professor Martin Blunt. He is a professor of petroleum engineering at the Imperial College London. His research interests are in multi-phase flow in porous media with many applications. He performs experimental, theoretical, and numerical research into many aspects of flow and transport in porous systems. He is distinguished for pioneering techniques to predict the underground flow of oil, water, and gas with application to improved oil recovery, contaminant transport, and carbon dioxide storage. He is editor-in-chief of the Journal of Transport in Porous Media with over 250 scientific publications and is a fellow of the Royal Academy of Engineering and the Royal Society. So once again, welcome, Professor Blunt. Thank you so much for accepting our invitation, and please feel free to start your lecture.
Okay, well, thank you very much for that kind invitation, and I will put my slides up. Okay, so hopefully you can hear me and you can see the slides. So I'm going to talk about flow in porous media in the energy transition. As was said in the introduction, I'm a professor in the Department of Earth Science and Engineering at Imperial College London. And before I start, I'd like to acknowledge the wonderful group of students and postdocs and other colleagues that I've had the great fortune to work with and whose work I'm going to describe today. And you can see some of our research group here in celebratory mood after one of our PhD students had graduated. But I'm actually going to start with a bit of context, actually. A bit of context. I'm not a professor of petroleum engineering anymore. I'm a professor of flow in porous media. And there's a reason for that, and it's driven some of our research directions recently. So if we look here at this picture, this is a statue of Queen Victoria that's in the main entrance to Imperial College. And the week actually before we closed down for COVID, there was a sit-in, an environmental sit-in, complaining about Imperial's links to the fossil fuel industry. So in fact, we now have a socially responsible investment strategy. And principally what it means is that we do not do any teaching and research that is related to the finding or extraction of fossil fuels. We can still receive, indeed we do, still receive money from the fossil fuel industry, but that has to be moving towards net zero. So it has to be about decarbonisation. And that's true, as I said, of our research funding, but also of our teaching. So here's the Royal School of Mines. This is the building in which I'm sitting at the moment, in which we do our teaching and research. And we have been teaching petroleum engineering for more than 100 years, particularly at master's level. And what we've done is we've changed that teaching. We've moved away from, again, looking for exploration and exploitation of hydrocarbon resources, but still retaining fundamental skills in subsurface geoscience and engineering, but also with a computational aspect. So what we have now is an MSc on machine learning and data science applied to geoenergy. And that's just one of a number of offerings that we have with a computational component, and then applying those skills to various scientific challenges of this century. And the particular challenge I'm going to be talking about today is how we apply the science of flow in porous media to understand the energy transition. So it's all part of an effort not just to educate a large number of students who are computationally skilled and then use those skills to try and solve the major challenges of this century, but also to address the gender imbalance in computational subjects. So I don't know what it's like in Brazil, but certainly in the UK, and that's certainly true of most Western countries, computational science degrees are about 3/4 men. And so what we're trying to do is actually educate equal numbers of men and women. And we've named this the Ada Lovelace Academy after Ada Lovelace, who was a Victorian scientist who's credited with developing the first computer algorithm and being the first computer scientist. Okay, so that's a sort of little bit of background of where I'm sitting and where we stand with Imperial College London. But now let's talk about the science. So We're not really going down to the atomic level, but we're certainly going down to the pore scale. So what we look at is flow and porous media as a scientific discipline in its own right, and then look at the rich variety of applications related to that. So porous media are any solid object that has holes. Actually, we're interested technically in permeable media, that is where those holes connect, so we can have fluid flow. And there are a large number of natural and manufactured settings in which you see flow and porous media. Obviously, rainfall, agriculture, soils, plants themselves are porous media. When you made your morning coffee, that's a porous media problem. Manufactured materials as well. Okay, all of these are porous media. Obviously, the focus of today's presentation will be principally natural porous media, sedimentary rock deep underground. That rock naturally will contain water, salty water at depth. It's also where we do find oil and gas, but it's also where we, as part of the energy transition, which I'm just about to talk about, would store carbon dioxide, hydrogen, or indeed water for storing thermal energy. So what do I mean by CO2 storage? So at the moment, the world is emitting about 35 gigatons of CO2 each year. And obviously that is the principal cause of climate change. So if we're going to prevent dangerous climate change, there are basically two things to do: emit less, right? So be more energy efficient, move away from fossil fuels to renewables. And of course, we're doing that. But the reality is that we are going to continue to emit some CO2 unless we deal with it. And we may find ourselves in a situation where we're having to limit climate change, which means we need to take CO2 out of the atmosphere. So what we have here is date and the amount of CO2 we will need to collect and store deep underground if we're going to prevent dangerous climate change. Now, of course, we don't know what's going to happen in the future. Okay, so we have a number of scenarios here, but every single scenario says by about 2050, we are storing somewhere between 5 and 30 gigatons a year. So that's actually comparable to how much we're emitting. So it's a big chunk. And most assessments say that is absolutely vital. Without carbon capture and storage, okay, we're going to be more energy efficient, we're going to have renewables, that's all great, but we're still going to be emitting CO2, right? And so we're still damaging the climate. So we need to deal with those emissions. We are, funnily enough, potentially on track, although those graphs always seem to be starting from zero now. It's not zero. We are currently storing about 30 megatons a year. So most people will notice straight away that we are 2 or 3 orders of magnitude adrift. But if we look at this globally in terms of capacity and what we're actually storing, we have growth rates of around 8% a year. If we were at least to maintain or even accelerate that, sort of 10% growth rates or more sustained over the next 30 years should be sufficient actually to meet those targets. In the UK, we're blessed with large storage resources, basically sedimentary basins underneath the North Sea. And so in terms of capacity, again, it looks like we will be able to grow capacity at a sufficiently rapid rate to meet our decarbonisation targets. Now, how this relates to the oil industry. So here's just a quote from BP. I'm just using this as an example. Most Western oil companies have made similar statements. So this is from Bernard Looney 4 years ago. And he's saying here that BP has an aspiration to be net zero by 2050. And that's not removing the emissions, that they make directly in finding and extracting oil and gas. It's also to deal with the emissions when that oil and gas, when those products are burnt, okay? And the only way in which you can do that is through large-scale carbon capture and storage. However, it is a challenge. So I'm not going to say it's easy, and that's why we need to do further research and understand this process. So here's a quote from Saudi Aramco. I'm just singling out Saudi Aramco because it's the world's largest oil company. Okay, so what are they doing? Here's an announcement to store 9 megatons a year by 2027. So that's pretty good. If we're at 30, and that's another 9. So it's not an insubstantial commitment, but it's a drop in the ocean. So if we look here, 1 barrel of oil releases about half a ton of CO2. I know I'm mixing units, but it's just the way of thinking about it. So Saudi Aramco's products, the oil and gas they produce, is 5 megatons per day, not per year, per day. So these plans are only 0.5%. So, and that's ignoring all other associated emissions with production, transport, and refining. So these plans need to be scaled up by a factor of 200 by 2050 to be net zero. And also, if you look at the wording here, potentially up to. So it's not even really a firm commitment to do 9 megatons. 9 megatons maybe if everything checks out. But actually the scale of the challenge is much bigger. So it's not wrong that we're starting, and these are significant projects, but we do need to really accelerate those projects. So I'll give you an example. What was going to be the world's largest CO2 storage project, the Gorgon project, offshore Australia. So it's separating out CO2 and injecting that, operated by Chevron. Again, 7 megatons have been stored, so in the last 4 years. So again, substantial. But actually, that's not, they are in fact not storing all the CO2 that's emitted. In fact, it's less than half of what was planned, and that's because of operational issues. So, there is a challenge, and we need to rise to that challenge. And now just a few slides to say it's not just CO2 storage that we work on. If we do move towards a renewables economy, we're going to need to store energy, right? So hydrocarbons are fantastic. They're a great energy store. Renewables are intermittent, and there are daily and seasonal fluctuations both in supply and demand. So we can store that energy as thermal energy, compressed gases, or we have electrolysis to form hydrogen. And if you crunch the numbers, actually, really the two things that are going to work is using hydrogen as an energy store, much the same way as we use natural gas nowadays. And also thermal energy, because we have a lot of relatively low-grade heat. So for heating and cooling, that's going to work. And basically, the only places where we can deal with gigaton style storage, there are lots of other things we can do. We can keep hydrogen in tanks, or you name it, but that scale has to be deep underground. That's the only place where we have that sort of capacity. So CO2 storage, groundwater use, obviously, as we have a growing world's population and we're climate stressed, that's actually rather important. Geothermal energy, okay, the storage of hydrogen underground, these are all flow and porous media problems, but also with manufactured devices. So I spoke a little bit about making hydrogen from excess renewable electricity, and then we can combine the hydrogen to create electricity in a fuel cell. These are actually flow and porous media problems. Okay, they're electrochemical problems as well, but all of them have a porous layer, gas diffusion layer it's called. The solid conducts electricity because you have to have an electrical circuit, but the pore space must allow the flow of water and gases. Both, basically, you have water that's split into hydrogen and oxygen, or hydrogen and oxygen that combine to form water, and you need those two phases to be flowing through the pore space. Other manufactured situations, packed bed reactors. So when we manufacture any chemicals, it's normally through a packed bed reactor. That's a porous medium. Catalysis, now we are getting down to the molecular scale. It's actually less of my interest. Again, we have porous media, membrane separation of gases, for instance, and particularly how do we separate out the CO2 in the first place? Again, another porous medium problem. So hopefully at this stage, flow and porous media is important, and you also know that it has a big role to play in our efforts to decarbonize our energy system. So what do we actually do at Imperial College? So the basis of this to begin with is experiments and imaging experiments. So many of you might be familiar with this picture here. This is a medical X-ray scanner. So it's used obviously to image people, but we can do it to image rocks. That's fine. The problem is the resolution isn't good enough to get down to where the physics is. The physics is at the pore scale, and the pore scale is sort of micron scale, right? So it's not molecular scale, but it's micron scale. So to do that, that's not a problem with X-rays. X-rays have a very short wavelength, so we can definitely image it, but we need to have the source and the detector close together. So we need to look at a smaller sample, normally samples that are now about 5 to 15 millimeters in diameter. okay, several centimeters long. You will also notice in this instrument, that's the X-ray source. It's wrapped in this gold jacket. What we can do is we can impose the conditions of high temperature and pressure that you might see underground, and we can look at not just the pore space of the rock, but the fluid flow within the rock. The only problem with this is to take an image in our laboratories, and we have these scanners in our laboratories, takes several hours. So you can only really look at a steady state. You can't look at the dynamics of flow. To look at the dynamics, you need to just take the images more rapidly. So for that, you need a synchrotron. A synchrotron is where you accelerate electrons near the speed of light, and they give this very bright beam of X-rays, as shown here. Okay, it goes through the sample. We can now get down to 1 second time resolution. And I know in Brazil, there's the Sirius light source that's coming on stream that actually will probably be the world's most advanced facility for time-resolved tomography. So that's fantastic as an opportunity. And it's like having X-ray spectacles, but even better because you can see in 3 dimensions. Okay, so here's an illustration of what we do. Here is the carbonate rock, an oolite. This is about 1 millimeter across. And this is an experiment. And this is just a 3-dimensional image that we're looking through, and then some fancy image processing. So you can see the calcite grains are the sort of circular things. And then what do we see here within the pore space? That's carbon dioxide trapped within the pore space of the rock. The different colors are just showing discrete ganglia or blobs of carbon dioxide in the pore space. One of the things we're really interested in is wettability, or the contact angle. So we're going to look at that. So just to show, we've looked at one blob here, and we're at sub-millimeter level. So the carbon dioxide is in the center, the brine, the salty water, is in blue, and the rock is showed in red. Now what we do is we look at the 3-phase contact loops, which are where the 2 fluid phases hit the solid, and that's what's shown in yellow here. To quantify wettability, by which we mean the angle at which the 2 fluids contact the solid, we take a plane perpendicular. So we can do this now automatically. So we have a code, we create an image like this, we segment the image so we identify phases, and then we can automatically calculate the contact angles. So here it is. This is the CO2, this is the brine, this is the solid. Actually, traditionally, we measure contact angle through the denser phase, through the brine. So we see a contact angle of about 45 degrees. And we see the water, therefore, it's water wet. The water curves round to contact the solid. So the water likes the solid. Actually, the CO2 is the non-wetting phase. Now, of course, there's lots we do. We've had this facility for around 10 years now. But in general, there are actually 2 things we're most interested in. One is you want something trapped in the pore space. So you want one phase to stay there. Okay. The obvious example is CO2 storage. You put CO2 underground into a porous medium, and you want it to be trapped in the pore space, actually, like I've just shown. The other example that unfortunately I think we're all too familiar with in recent years is surgical masks. Okay, that's a porous medium. You need air to flow through it so you can breathe, but you do want to trap droplets from you or droplets of water from other people that may contain a nasty virus. Okay, so you want to trap things. The alternative is actually the opposite. You actually want things to flow, right? And particularly you want more than one fluid phase to flow through your pore space. Classic actually is oil recovery. I inject water and I want to get as much oil out as possible. Okay. Fuel cells electrolyzers are also that example where we have a gas and water, and those have to flow through that gas diffusion layer. Okay. The other one is actually hydrogen storage, because we inject hydrogen and then we want to produce it again because we want to use the hydrogen. Okay, so these are all these examples. They're controlled by the pore structure, of course, but also the wettability. The contact angle is really our emphasis. And we do multi-scale, multi-physics experiments and modeling to analyze this. And I'm just going to show a few examples. So this subject, basically where we take images and we do both image analysis and modeling, is called digital rocks. Okay. And so there are a number of things we've sort of discovered from this, and we've just made these discoveries principally through the experiments, not so much from fancy modeling. So I'm not going to say so much about modeling, even though you know, my real expertise is in modeling. Okay, so I'm going to show trapping in CO2 storage. We've also shown that we tend to get intermittent flow, so fluctuating pore space occupancy, even at quite low flow rates. I'm not going to say much about that. I'm going to talk about what leads to good recovery, so what leads to good flow and minimal surfaces. I'm going to talk a little bit about three-phase flow, where we store CO2 in a depleted oil field. And I'm also going to look at hysteresis and trapping in gas storage. That's our most recent work. And again, is very significant for these applications. So let's look at the first one. So CO2 storage. So here's an image. CO2 is injected into a rock like it would be deep underground. The blue is CO2 that's actually connected through the wider pore spaces. The CO2 can flow. So from an environmental perspective, immediately there's a concern. I inject the CO2 underground, but it can move. So it will tend to move upwards and sideways, and maybe it's going to escape. So it's all a bit of a waste of time. You put it in and it comes back out. Actually, that isn't what happens. Actually, from a petroleum background, I think it's obvious. Okay, as the CO2 migrates through the pore space, it's replaced by water. The water is the wetting phase, and it traps the non-wetting phase in the centers of the large pores. So after water flooding, okay, the different colors here are actually trapped ganglia, and we get a significant amount of trapping. So here is the saturation you put in. This is how much you've trapped. With CO2, in this particular example, it's about 50%, and you trap about almost 30%. Now, the remaining 20% continues to migrate, but again, that can be trapped. So in fact, injecting CO2, and then as it migrates, basically at the trailing edge, water is trapping the CO2, is an effective and relatively rapid mechanism for rendering the CO2 immobile in the pore space. So that's good. Now let's look at this a bit more generally. And again, just flow in porous media. Don't get fixated with the application. Just think about it as a scientific discipline. So we can, we're interested in flow in porous media, and we're interested in interfaces between phases. And we can define what's called a curvature. So I think you're aware of this. If I draw a smooth line, at any point, I can fit a circle to it. R is the radius of curvature. Kappa, which is the inverse, is the curvature itself. If I have a smooth surface, hopefully intuitively, you can see that it makes sense to say that there are actually two radii of curvature, and actually they're defined in orthogonal directions. And not only can they different in magnitude, but they can be different in sign. Now you might say, how can I have a negative radius? Well, imagine as an apple of ball shape, okay, it's curved one way and the other way, and it looks the same. Okay, that's a sphere. But a pear-shaped, what do I mean by a pear shape, is if I slice it this way, okay, it's a circle. But the whole idea of a pear shape is the other way, the curvature goes in the other direction. That is, the air bulges into the pear, not the pear bulging into the air. So it has another radius of curvature, but actually that's a negative curvature. Okay. So what we can define, and it turns out mathematically, this is a complete geometric characterization of the fluids in the pore space. Basically, volume, the saturation, so how much stuff you have. The interfacial area, and that's obviously going to govern interfacial properties. The curvature, which is the sum of the two principal curvatures, that actually, from the Young-Laplace equation, gives me the capillary pressure, gives me the pressure difference between the phases. Okay, so immediately we have something useful. But we have two curvatures, so two independent things. I can define two other quantities from it. So Gaussian curvature is the product of those two. And you might say, okay, so what? That's just maths. But it turns out there's something rather remarkable about this, is that the integral of the Gaussian curvature over a surface is 4 pi times an integer. And it doesn't matter what the shape is. So it's the Euler characteristics, number of objects minus any loops in the objects plus holes. So it's a topological characteristic. So imagine I have a sphere, okay, of radius r. The Gaussian curvature is 1 over r times 1 over r, because those are the two curvatures, so 1 over r squared. The surface of a sphere is 4 pi r squared, so you do that integral, it's 4 pi. So the Euler characteristic is 1. But the point is, the Euler characteristic is 1 if I have a, say, a cube, if you can see the video, right? It's still 1, still topologically the same. Or if I make any object that's topologically equivalent. If I make two objects, the Euler characteristic is 2. If I've got 3, it's 3. Now, if I put a hole in the object, well, actually, it's not a hole. Actually, technically, it's a loop, okay? Then the Euler characteristic goes down by 1. If I put 2 loops, it becomes negative, okay? Lots of loops, and it becomes more negative. So in fact, it's about connectivity. Where the Euler characteristic is high, you've got lots of discrete objects, it's trapped. The Euler characteristic is negative, you've got lots of redundant loops, you're actually well connected in the pore space. So that actually solves the conundrum. What we need, we know what we need for trapping. You need one phase to be wetting, and the non-wetting phase is trapped in the pore space. We have ball-shaped fluid interfaces. The radii of curvature are equal and of the same sign. The Gaussian curvature is as positive as possible. The Euler characteristic is positive. That's actually already known. The opposite is actually negative Gaussian curvature. So one curvature is positive, the other is negative. And actually, if they're equal magnitude but opposite sign, is ideal. Turns out mathematically that is seen in what's called the mixed wet state with pinned interfaces. So if we imagine a rock, right, to begin with, which has been in contact with crude oil, the surfaces that have been in contact with oil are rendered oil wet, hydrophobic, and where there's just water, it's hydrophilic. If you have an interface between the two, this three-phase contact loop is actually pinned in place, and the minimization of energy actually gives us a minimal surface. Doesn't mean it's a flat surface, but it's where you've got two equal and opposite radii of curvature. So the question is, do we see these, and does it lead to good recovery? And we will start with a petroleum application, because that's where we first saw it. So here is an image of oil within a sandstone. And what's shown in blue is the interface between oil and water. And although, you know, it's not that easy to see, it's sort of ball-shaped interfaces. The curvature is positive, the capillary pressure is positive, and the oil is trapped. Checks out. Now what we did is we took the same sandstone, but we put it in contact with crude oil. But we didn't make all the surfaces strongly oil wet. There's what's known as mixed wettability. We see now the interfaces are much more complex, much larger surface area. The average curvature is almost exactly 0. So these are minimal surfaces. Now you'll say, okay, but does that lead to favorable recovery? Actually, it does. So here's another example. This may be a bit more relevant, you know, from a Brazilian context. This is actually, though, from a reservoir from the Middle East, but it is a carbonate. So we've got a complex carbonate structure. These are the raw two-dimensional cross-sections of three-dimensional images. We actually segment them into 3 phases. So that's oil, water, and the rock in white. So to begin with, we got the rock almost full of oil. Obviously, there's some water trapped in the corners of the pore space. As I inject more water, the fractional flow is the fraction of the volume injected that is water. So we start at 0 and we keep increasing until we get to 1. And we can see, oh, we've covered most of the oil. That's fantastic. So you can immediately see just visually. It's amazing. In terms of the flow characteristics, the capillary pressure would be exactly 0 if it's a minimal surface. It's slightly negative, so we have to push the water in, but it's very low capillary pressures. Right? For anyone who knows about typical capillary pressures in a strongly wetting state, these are really low. Right? The relative permeability characteristics, and again, if you're not an expert in this area, it's difficult to understand. But basically what happens is the water is retained within the pore space, not terribly well connected. The oil can be pushed out, and it's only right at the end that you will trap some oil, okay? It's only right at the end the water flows. So for recovery, it's good. You inject the water, it's held back in the pore space, the oil is produced. So this is actually a good case for recovery. Not every case is like this, but in this specific case, it is. Now let's look at these gas diffusion layers. How do they work? Well, this has been done empirically. It wasn't actually designed specifically with this in mind, but the carbon fibers that conduct electricity are water wet naturally. So if you had a fuel cell, it wouldn't work because you generate water, it's water wet, it would retain the water in the pore space, and basically the device would stop working. So what you do is you partially, and this is the key thing, you partially coat the fibers with a plastic, PTFE. That actually helps bind the fibers together, so it gives it mechanical strength. But more importantly, you have regions which are water wet, and then a region coated with plastic that's oil wet or hydrophobic. The interfaces between the air and the water reside at that boundary. The mean curvature is almost exactly 0. So here's different amounts of coating. It's only when it's super well coated, it begins to become actually too hydrophobic. But there's gas and water in the pore space. The key thing is there's virtually no pressure difference between them. So air can move in, water can move out. You don't have to build up a pressure to get them moving. They move past each other with zero pressure between them. Okay, and that's ideal for operation. So this was done empirically, but this is why it works. And obviously, we can design it for other systems. Okay, now let's look at another application. The first real commercial applications of carbon capture and storage are for enhanced oil recovery, where you're putting the CO2 into an oil field. And actually, frankly, I think this is a good idea because you are going to end up with potentially gigatons of CO2 stored underground in depleted oil fields. Okay, so what we're showing here is the CO2 injected from the top. This is about 4 millimeters. This is with time-resolved imaging, and it's oil wet. So this is an oil reservoir where the oil has been in contact with the surfaces. What happens to the CO2? Well, if you ask any reservoir engineer, you know, talk to Petrobras or BP or Shell or anywhere, pick up a textbook. CO2 goes through the large pore spaces. It's the most non-wetting phase. It's terrible. CO2 just channels. Bit of a disaster. Don't do it. That's actually not what happens when we can actually see. What you see here with these different colors is the CO2 is disconnected. So the CO2 is moving through the pore space and it's never connected. And it's not going through the biggest pores. The reason is that water is the non-wetting phase. It's oil wet. This is near miscible gas injection. The CO2 has properties similar to the oil. The CO2 is actually what's known as intermediate wet. And it progresses by CO2 moves in. It will then push out some water that will displace some oil that may displace some more CO2. You get this chain of displacements, and the CO2 is moving as a discontinuous phase. The big advantage here is stop injecting, it's all trapped. It's really good for storage. So our conventional models actually rather overemphasize how much CO2 might channel. Our suggestion is you just inject CO2 and it can be stored. And that's then quantified both with the oiler characteristic and with the relative permeability, the ability to flow. The oil is actually well connected. It's connected everywhere in the nooks and crannies and the corners of the pore space because it's wetting. Negative oiler characteristic, reasonable relative permeability. Water is the most non-wetting phase, so it can get trapped. So its oiler characteristic is positive. But when it does connect, it's in the big pores, so it can flow. The gas, however, is poorly connected and poorly flows because it's in these disconnected clusters. So, and that's what you want. You want the CO2 to be retained in the pore space. And if you want to make some money, you want the oil to come out. Okay. Now, the last bit of physics I'm going to talk about, so that was the last application, was to do with gas storage. So it looks like we inject CO2 or hydrogen into the pore space and it gets trapped, which is good for CO2 storage, not so good for hydrogen storage. But there's another thing that we hadn't looked at until recently, is a process called Oswald ripening. And you'd see this anyway if you had a fizzy drink and you had lots of bubbles. In the end, you just get one big bubble. So why is that? You have a bubble of gas. The pressure in the gas is the pressure in the water plus capillary pressure, which is related to curvature. The amount of gas that dissolves in the water is proportional to pressure. So a smaller bubble with a smaller radius of curvature, higher capillary pressure, slightly more dissolves here than here. This sets up a concentration gradient. So we can have a flux due to Fick's law, and we can look at the typical change in concentration using Laplace. So you use a lot of your sort of university physics. And what this does is it leads to a flux. So the small bubbles disappear and the big ones grow. Now, in a porous medium, it's not quite like that because it's not to do with the size of the bubble. It's to do with the curvature, which is to do with the pore structure and wettability. So it's a subtle thing. There are multiple stages of equilibrium. It's not that there's no trapping or we get one big bubble, but you do get a rearrangement of the fluids in the pore space. You can estimate the time scale for this. And the time scale at the field scale is huge. But locally, within sort of days to weeks to possibly months, you get a rearrangement of the fluids in the pore space to maintain equilibrium of the gas in the aqueous phase. So we can see this. So here's an example. This is now hydrogen as a specific example. Initially, here's the hydrogen, and then after you wait 16 hours, you see it's rearranged with a tendency to reconnect. We look at these Euler characteristics all the time. The Euler characteristic goes down, which means better connected. And in fact, this diagram shows there's a little vertical thing, it shows that the hydrogen rearranges and then you have a connected cluster that can flow. So there is less trapping. So what's nice about this is actually there's a relatively quick fix. So traditional measurements actually normally done very quickly, or sort of oil company type measurements. So there's no account for transport in the aqueous phase. And in fact, that overestimates the amount of trapping. However, I'm not saying there's no trapping, because that's what I started with at the beginning of this presentation. There's just less. But actually, it's very easy from a modeling perspective or theoretical perspective. It's basically a percolation process where you have capillary equilibrium everywhere, and there's no real trapping in the sense that a small ganglion can disappear through this transport. So we can model this and we can correct traditional measurements. So that's what we've done. We do a lot of pore network modeling. So we represent the pore space of the rock topologically by a lattice of pore spaces, wide pore spaces and throats that are restrictions. Done appropriately, these models can actually predict experimental measurements. So here's a capillary pressure as I inject, say, hydrogen, and then I displace the hydrogen with water, and we're trapping about 40% in the pore space, and we can do repeated loops, and that looks great. But actually, if we allow for this Oswald ripening process, we get a similar behavior, but there's just less trapping. Same with the relative permeabilities, with the flow properties. Again, we can make predictions that match experiments. That's great. But now if we account for this Oswald ripening process, we're just getting less trapping. Okay, so the relative permeabilities are extended. And the way in which we can account for this, so we can actually correct, we can take a measurement rapidly and then correct it to what it should be, is basically to plot everything as a function of a normalized saturation. So on a normalized saturation scale, we seem to have a universal curve, and all we need is actually this parameter, which is how much is trapped eventually. And that can be modeled, we can predict it, or actually we can measure it. So we can trap something and then wait for a week. Some things reconnect, so then we can displace a little bit more. So that's what we've done, and empirically, current models are probably overestimating the amount of trapping by somewhere around 20–25%. So I'm near the end now. Hopefully some time for questions. So we are moving a little bit away from looking at, quotes, natural systems to manufactured systems, where we can actually talk about the design, so we can change things. So we're looking at heat and mass transfer for reactor design. So here's an example where we're heating the sides of a packed bed, and that's obviously where it's the sides, it's hotter, and so the water viscosity is lower, so there's more rapid flow. And how do we design this to optimize reactions? And so that is now our emphasis, looking at manufactured media, but also natural systems. So here are just some of the highlights. Surgical masks, by the way, if you want to repel droplets, you make them out of plastic fibers. So proper surgical masks have a layer that is basically plastic fibers, hydrophobic. The problem there is with a surgical mask, you also have very fine droplets. They're sufficiently fine they can just fly through the porous medium. You can't make the mesh tighter because then you won't be able to breathe. So actually you have a hydrophobic layer and then a hydrophilic layer that electrically attracts the smallest droplets. Okay, fuel cells and electrolyzers is this mix of wettability, which is the reason why it works. Okay, that's been seen empirically, but the idea is, could we extend it to other systems where you want to have flow of more than one phase? In CCS, we're looking at disconnected flow, particularly for storage in depleted oil fields. Okay, and the idea is then to design better processes, both in the subsurface and in manufactured materials. So does it matter? A wide range of very important applications associated with flow and porous media, even as we move away from looking specifically at hydrocarbon production. I'd like to end now. I'd like to acknowledge the sponsor of the work, and you notice these are symbols of oil companies. So we do still receive funding from the oil industry, but it's all related to moving towards net zero. I'd like to plug my textbook. Actually, everything I've discussed today isn't in the textbook. So, things have moved on. This is all recent stuff. I have a YouTube channel for people who are interested in learning more about flow and porous media. But hopefully that's given you an introduction to some of the things we do. and I'm happy to entertain any questions.